let's try our read, imagine, sketch again. We have Mini Cooper, 600 kilograms. We have a driver of 80 kilograms. Skids to a stop. Stop means velocity 0, right? It's the same two things, except now their velocity is 0. Skids to a stop in 1.1 seconds. You know what? That's a time interval. If the road applies an average force of 6,600 newtons, let's see, on the car, so force of road on car, 6,600 newtons. What was the speed when the what was the speed when the brakes were applied? So what was the speed? Sounds like we're looking for a velocity here. Now, my first attempt at imagining and sketching turned out pretty good because I'm experienced at this. How do you get better? By practicing. And by looking at the work of someone more experienced than you. But really all I did was make some simple choices, and I just sketched things as they came up in the problem, and we end up with something that's a pretty good sketch of a solution to this problem. So, the tough decision is always, should I approach this problem, should I treat this problem as a system in which the total momentum is constant? Or should I treat this problem as a situation in which something from outside is changing the momentum of system objects? Let's look at what we know, shall we? There's many ways to solve all of this. Try them all. Let's see, what do we know? We know, is there any reason we can't treat the car and the driver as a single object? Sure. They're moving together the whole time, right? They're moving together the whole time. So why can't I just say that this is one object with a mass of 680 kilograms? It works out fine if you want to treat them different, but I'm about saving trouble, and we might as well demonstrate the benefit of imagination. A little extra imagination saves us a certain amount of calculation. So we'll call these together the car. We won't bother about the driver. Driver's not interesting, although his mass is part of the mass of the system. So do I know the initial momentum of the car? No, I don't. Although I know its mass, I don't know its velocity. Do I know the final momentum of the car? Yup, I do. I know its mass and its velocity. When you're reading and imagining, as soon as it said it was stopped, we thought, oh, stop, velocity is 0. I know the momentum of anything with a velocity of 0. Let's go toward a bar chart. We've got, if we put the car here and the car here, let's write in what we know. The final momentum of the car is definitely 0. The initial momentum of the car is, well, it's definitely something, right? Can I put a number in the delta P column? Ah, yes, we can. All right. We know that a change in momentum can occur as a result of an impulse exerted by some external object. And I can calculate the amount of that impulse if I know the net external force exerted on a system object, add all the unbalanced forces exerted by external objects, and multiply it by the time period over which that impulse was exerted. And, hey, bingo, the road on the car is the only external force, so I know this quantity. And during the time it skids, is that when that force is applied, I know this. That means I know delta P. So this is some quantity I can find out. I haven't calculated it yet, but we know what that bar is going to be. So now we've got all bars but one. So now we know that we're going to know the size of that bar. Are you with me? Numbers adding up? Anything unaccounted for? Let's calculate something we know. Let's calculate the value of that delta. Delta P, 6,600 newtons times 1.1 seconds comes out to about 7,200 kilogram meters per second. So this bar is, oh wait. As soon as we start calculating with forces or momentums, that's a direction quantity. So let's go back to our sketch and decide on a direction. Let's see. Let's call this positive. See what happens. That means let's check all our direction quantities. This velocity is going to be something positive. What other quantities here have direction? Force is a direction quantity.
Negative.
So this is going to be a negative force, because the force of the road on the car is in this direction to cause the delta V, to cause the slow down, right? So that means that we need a negative here because there's a negative here. Oh, and that means our bar chart is backwards, but that's okay. You can fake it or redraw it, whatever you want, but we've done a negative, so let's do a negative. This is negative 7260, final velocity. So that means that the initial total momentum of the car had to be that's the short version. Because we did some extra work in our imagination, I can just stare at that and tell the value of the initial momentum of the car. If you wanted to do it the long way with math, you could rearrange these to get the initial momentum of the car equals the final momentum of the car minus the change in momentum, 0 minus negative 7260 equals 7260. So we've almost got it. The question, however, is what's the velocity of the car? Again, definition of momentum. Rearrange to solve for velocity. So the initial velocity of the car would be equal to the car's initial momentum times the mass of the car, 7260 divided by 680 kilograms. That comes out to 10.7 meters per second. Evaluate for reasonableness. Is a plus sign correct? Yes, that would mean it's going in this direction. That's what we expect. 10 meters per second, about 30 feet in a second, 1001 Well, that's the car's not speeding on the highway, but that certainly is a reasonable speed for a car. It works out to about 24 miles an hour. So make a note to that effect on your car. The car's not going super fast, but this is reasonable. Everything checks out. Questions from the people in the room?